So I put on the Professor McKinney's stream will return shortly. Now. The audio? Okay, so what I wanted to kind of talk about today, a little bit more about functions and really how parameter passing works, and then also really hit recursion and really look at how that really works. So, all right, let's get to it. So functions, right? If we go back to something like this, so this was this stupid example that we did last time, right? Or whenever, right? If I write a function that, and I had even paused a few minutes to let everybody get here, and then right when I give up, you guys show up. Yeah, yeah. Well, Caleb's here, so we can get started. Um, okay, so I had this stupid function that all it's going to do is square a number, right? Nothing particularly glorious from a mathematical perspective, but we were doing this as a function. So if I want to pass, so for example here, if I wanted to write in C a function, long int square of long int, okay, whatever data types come in and out, in this case, because I decided to make these long ints, so 64-bit ints, I'm passing a 64-bit number in, and I'm getting a 64-bit answer out, okay? And so in C, that's how we would say it, right? Okay, great. In assembly, what we need to do is, well, whether or not the data coming in is a long int, a float, a pointer, something else, right? How do we know what kind of thing is coming in? Well, where do long ints live in the processor? Just one, right? The X registers, right, which are the 64-bit versions, okay? Not the W's, which are just the lower 32-bit halves of those, okay? And not S or D, which is where floating point stuff goes, and so on, okay? So we know, looking at the assembly for the square function here, that it's accepting a 64-bit integer because, rather than a 32-bit one, because it's using the X registers, not the W ones, okay? And in this case, we also know that it only takes in a single number because it's only using anything out of X0, okay? And so if I were to pass two values to a function, like say, write a function that adds two numbers and returns the sum, I mean, I would never actually do that, but then where do the two input numbers need to go before I call the function? They need to go into registers 0 and 1. Okay, you always start at register 0 for parameter passing. Okay, all right, now, you both said 1 and 2, and why were you saying that? Yeah, you always put, okay, because you always put the address of a format string for printing in x0. But the reason you're doing that is because print0 is a function, and you're passing arguments to that function. And you start passing arguments in x0 or w0. Okay, it's just that in that case, the address of the format string, which is a pointer, right, is one of those arguments. Okay, so whenever you're writing a function in C, that takes in, like, let's say it took in 6 values. Those values would need to be placed in register 0, 1, 2, 3, 4, and 5. That's the convention for where you should expect to put inputs to functions that you write or that somebody else has written. Okay, so for example, well, okay, I wrote this square function, which is kind of stupid, but there are square root functions built into the hardware. Okay, or what was we used a square root function, and some of you actually used the power function in assignment, what was it, 4, the structs one, right? Okay, so when you used the square root function, that was actually using software square root, I think, okay, which is why we were using math.h and compiling with that extra little flag, okay, and that is a function. Well, where should that function expect its input? Okay, for a square root, obviously there's only one input. It should expect it in x0, or actually in that case it was d0 because it was for floats. And where should you expect the output from a function? If a function outputs a single number, where should that number be expected to be? x0 or s0 or d0, but the 0th register. Okay, so it's always, the parameters are always passed in those chunks of registers. If you need more inputs than 8, okay, that's going to be kind of a squirrely function, but you could need it. Then you have to start using the data stack. I mean, I would have to contrive an example where we would need that many inputs, but I could, right? Okay, so, right, this is that. Now, this parameter passing thing, by the way, is not a hardware requirement. This is a Linux requirement. Okay, and that's just the convention on parameter passing in Linux. Now, I've been talking with Matt, because Matt, has your new toy made it here yet? Not yet? Okay. Well, so Matt's laptop died. Uh, yeah, rest in peace. So he's getting a new one. And fortunately for him, as a Mac user, guess what just was announced 2 weeks ago? New MacBook Pros. So he's getting one. All right. No. And I cannot wait to get my hands on that thing because it's an ARM architecture processor, and I want to fire up assembly on that thing and see what's different about how you work with assembly on Mac OS versus in Linux. Okay. Now, I would imagine that the parameter passing convention is the same. Okay, and the reason is Mac OS is built on top of what? It's a Unix variant. It's built on top of BSD, Berkeley, right, which is a Unix variant. Okay, well, Linux is also a Unix variant, right? So I would expect that they have the same calling convention, but I could be wrong. We'll find out once your toy gets here and you let me have it. You did order 2, right? No? Okay. Yeah. Consider, well, if you give me one, it's actually tax deductible, right? Because I work for a 501c3, so it's a donation. Yeah. Um, yeah. So, have many of you guys seen the movie Contact? It's from the 90s, but like there's a big radio telescope array, and then they get this signal from outer space, and they decode it, and it tells them how to build a like wormhole traveling thing so they can go visit these other aliens. And anyway, there's this terrorist plot to blow it up, and uh, they blow it up, and then everybody's all crestfallen. But it turns out that the government has actually built a second one of them in secret, and one of the characters says, "First rule of government spending: why build one when you can have two for twice the price?" So, yeah, huh? Yeah, that one took a little bit too much setup for the humor, but okay. Okay. Anyway, so um, let's just remember the calling convention, right? Inputs go in X0 through X7, outputs come in X0 through X7. If there need to be more of those things, then you have to start using the stack, okay? Um, all right, so the function that I want to talk about today is actually something recursive, okay? Uh, we've done, like if we think back to when you guys did the Fibonacci's in C, right? You wrote two functions to do it, an iterative version and a recursive version, okay? And what did the recursive version look like? Well, it was, you know, if the input number is less than 2 or 1 or 0 or whatever, right? So you had a base case. And then what was the recursive step for the Fibonacci's, right? Fibonacci of n is equal to plus Fibonacci of n minus 2, okay? And then that called it itself, and it just kind of looped until eventually you hit the base case, and then you came your way back up, okay? All right, so that is assignment B, is to do that in assembly recursively. Okay, you've already done it in C, but let's look at, for sake of example, how would we do, well, what's another good example of a recursively defined thing besides the Fibonacci's? Yeah, the factorial function, okay? So let's look at the factorial function and see how we would implement that in assembly, and also how, when we start, like if we run this through GDB, how the recursion is actually really truly working. And yeah, hopefully that'll be clear. Okay, so let's see, we need data, we need text, and let me go ahead and save this real quick. Okay, so we'll call this fact.asm, and I'm going to define down here a function, okay, called fact, and then we'll do stuff. All right, so first part of any program, right? Don't talk about the program, right? Oh, while I'm thinking about this, because I just thought I'd point it out, because Farden ran into this. What's the exclamation mark do? Huh? Makes you surprised, or it's that instruction is really loud? Okay, no. So what the exclamation mark does is it basically changes whether or not the minus 16 happens before or after you store the pair, right? So it's, should we decrement the stack pointer and then put the data on, or should we put the data on and then decrement the stack pointer? In this case, the former is what we want, okay? And then on the back end, that means we need to pop the data off and then change the stack pointer. So if you forget that exclamation mark, then you get bad things happen, as Farden found out. That was literally the only problem with one of his programs, was that one symbol. Yeah, I mean, gosh, right, Farden? Okay, so anyway, so we got to have that, and then of course, what else do we need? right? That, okay. So wonderful. So let's, if we're going to call this function, right, we need to call it with a value in x0, okay? So let me, or w0, doesn't matter, right? So let me move x0, and let me just move the number 5 for sake of demonstration, okay? And then I'm going to branch and link to fact, okay? And the linking is going to become important in a moment, okay? It may not have been important with our stupid little square function before. Well, it actually was. But it's going to be super important to be linking here, okay? And we'll talk about when we get into GDB exactly what the linking part is doing, okay? Okay, so then we'll come back from the function and we'll put this in later. We'll print some stuff. We'll print the answer, okay? Okay, so first off then, let's get down here to our factorial function. And if I were to write this in C, what would it look like? I'd say something like long int fact of long int n. Let me put some comment bars here, right? What would I say here? Well, okay, I'll put the comments in later. What was the definition of the factorial function from a recursive standpoint? Well, what do we have to have in recursion just to make sure that it doesn't go on forever? When in some sort of base case or base cases, okay? And in the case of the factorial, what are the base cases or what is the base case? Depends on how you want to look at it. What's 0 factorial defined to be? 1. What's 1 factorial defined to be? 1. Okay, so we'll just say if the input value is less than or equal to 1, we'll return 1. Otherwise, we'll do the recursion. Okay, so we'll say, all right, if n is less than or equal to 1, return 1. Okay, else, what do we return? We return n times fact of n minus 1 factorial, or sorry, n minus 1 factorial, right? Because what's 5 factorial? 5 times whatever 4 factorial is. And what's 4 factorial? 4 times whatever 3 factorial is, and then you just keep doing this until you hit your base case, okay? Now, I mean, to be clear, would you ever actually want to compute factorials this way with this sort of recursive view? No, right? From a computational standpoint, it's horribly inefficient, right? A loop, a just iterative loop would be much better, okay? But it serves as a good example of the recursive structure without being too complicated. So that's why I'm using it as a good example. Okay. All right. So are we clear with the C part of it? That's what it would have looked like roughly. Yeah. Yes. Good. Any questions on the C part of it? No. Okay. All right. So basically, we want to implement this, but in assembly. Okay. So our input number we need to take in our input number in x0 because that's the calling convention for functions, okay? And that's a Linux thing, not an ARM thing. And then accordingly, we need to return our answer value also in x0. Again, that's the calling convention. Excuse me. Okay, so we need to first check, have we hit the base case? Okay, so is our number less than or equal to 1? Okay, so what do I need to do to compare it to a specific number? Yeah, I need to do a CMP command, okay? And then but what am I going to compare it to here? Okay, so where do I have to put 1? Well, okay, yeah, but let me actually put that in a register. Okay, so let's move x1, the number 1, and then let's compare x0 and x1. Okay, now, in which situation should we continue, and in which situation should we just quit because we have the base case? Right, okay, so let's do b dot g t, because we want greater than, not greater than or equal, okay, to, let's say, recursive case. Okay, just something like that. Okay, now you might say, wait a minute, didn't we say it was less than or equal to is the base case? Well, yes. Okay, so what's the opposite of less than or equal to? Greater than. Okay, so our recursive case will go down here. Okay, now if we do not go to the recursive case, that means we're doing our base case. What is the base case? That means the number that came in was less than or equal to 0 or 1. So we need to return 1. Okay. Where is the number 1 sitting at this moment? It's sitting in x1. Where does it need to be sitting? X0 to be returned. Okay. So we just need to move the contents of x1 to x0. Okay. Or we could have done, we could have also done this. Okay. Either way. Okay. In fact, I'll just leave it like that. Okay, so this is the base case. Okay, now our recursive case, okay, so are we cool with the base case part? First thing, we're just checking, are we in the base case or not? If so, just keep going. If not, jump to the recursive case, okay? And then what do we need to do down here? So in C, if I return 1, that's really the same as putting something in x0 through x7, whatever, and then the ret command, which would return us from the subroutine. Okay, so is that all right? Yes. So this, yeah, okay, good question, right? And well, this is what the whole point of the link register is. The main routine calls the fact function, which brings us down here. So when we hit this ret, it sends us back up to the line immediately after we called the fact function. Okay, in the same way that this ret in our main program returns us back up to the line immediately after our operating system called our function. Okay, so it returns control back to the OS. Okay, so is that okay? Yeah, okay. So so a return or a, terminate, kind of like the end of a loop, or sorry, the end of a function, if there's no returned value, in assembly, there's really a ret there someplace, okay? Okay, so that's our base case set. Good? Okay, now the recursive case. So here's sort of the issue, right? I've got the number in, okay? So let's say where 5 is coming in, right? What do I need to pass to the recursive case? X0. Right now it's in X0, okay? So right now 5 is in X0, okay? So in C, what would I do here? I'd say return in 5 times fact of n minus 1, okay? So the first thing I've got to do is compute n minus 1. right? I just need to take 1 away from 5. Okay, and then I need to pass that to my function. What's the problem, though? Well, I may have to recur some more, but where do I need to put the number 4 before I call this function? Okay, but what's in X0 right now? I can't have two things in the same register. That's a problem, right? So if I can't have two things in the same register, the number 5 I need to keep for later, right, when we actually do the multiplication. So if I need to save that number, but I can't leave it where it is in X0, what are my options? Okay, use the other registers that are preserved or store it on the stack. Okay, and in this case, we pretty much have to store it on the stack because there could be too many numbers, right? For 5 factorial, yeah, there's plenty of registers. I could store everything I need in the registers. But how do I know that that somebody's not going to come along and do 100 factorial, right? I don't, theoretically, okay? And so I pretty much I must use the stack here because we have way more memory than we have registers. Now, would we theoretically eventually run out of memory too? Well, yes, but there's way oodles more of that, right? Because on this processor, right, you have 32 64-bit registers. Well, how much RAM do you have? How much RAM is on our Pis? 4 gigabytes, right? That's way bigger, right? If we're going to hit 4 gigabytes worth of stack, like that ain't happening, right? That's a very bad day. Okay, if you're hitting 4 gigs of stack space, you're going to have a bad time. Okay. That's actually not the MK guy, Mr. Mackey, but it's the ski instructor when they all go to the ski resort and the parents get trapped in timeshare presentations the whole time and don't get to actually ski, and the kids just get to ski the whole time. Yeah, yeah. So, so if you ever go to a resort, don't get sucked into the timeshare presentations. Okay. So, okay. All right. So we need to preserve the number that's in X0 because we need to use it later. Okay. And we need to put it on the stack. Okay. So what should we do? Yeah, we should put it on the stack. Okay. So I'm going to store the register X0. No, the assembler doesn't care. I mean, I will just to, just for, no, but it makes it more readable, I think. Okay, I need to store this to the stack. Okay, now, 2 questions. I used str here, not stp. Why? I'm only storing one register. STP is if I'm storing a pair. In this case, I don't need to store a pair, so there's no worries. Okay, and why still minus 16? Even though I'm only storing 8 bytes worth of stuff. Yeah, because the stack pointer must be a multiple of 16. That is a hardware requirement. Yes. LDR is for load a single register, and LDP is for load pair. Mm-hmm. No. So if you need to store 4 things, you'd have to do it as 2 pairs, right? Yeah, there's no extended instruction for that. Okay, so I need to store the thing, and then on the other end of something, I need to pop it back off the stack. Okay, all right, now, what do I need to do to the number that's sitting in X0 before I call my function? Well, okay, so if the number is 5, what am I going to call the factorial function with next? 4, right? Oh, because I'm an idiot. Yeah, okay. I've got to subtract 1 from my input number, right? So let's subtract 1 from x0. Yes, it's a copying operation, not a move. Yeah, good point. So, yeah, so store just takes it from the register, puts it in memory, but that value is still in the register. Okay. Yeah. Okay, so take 1 away from the thing, and now I'm going to branch and link to my fact function. Okay, so this is basically saying, okay, compute the number n minus 1, and it's in x0, which is where the first input needs to go. Pass that to the fact function. Now, yes, we're already in the fact function, but that's okay. That's why this is recursion. Okay, so is that part okay? Now, the branch and link here is really important, okay? I'm not branching to the factorial function, I'm branching with link to the factorial function. And again, when we get into GDB, we'll see what's so important about the link register. Okay, good so far? Exactly, we have not. That's what's coming right now. Okay, yeah, so good point, right? In C, what did I say? Return n times fact of n minus 1, and that was it, right? It was all a single line. But I can't do all that in one instruction. So I have to do n minus 1 as a computation. I need to do fact of n minus 1 as a computation. I need to pop the number n back off the stack, so I have 5 ready to go. And actually, I don't want to put that in x0, as we'll see in a moment. Okay, and then I need to actually do the multiplication. Okay, all right, so where should I load the number 5 back off the stack to? I shouldn't put it in x0 because when I come out of the fact function, what's sitting in x0? An answer. Okay, and if I load something into x0, what have I just done to that answer? I've nuked it, right? So I shouldn't do that. So what would be a better choice for where to put the n number? How about x1? Okay. Okay, and now, as Owen suggests, we need to actually do the multiplication. Okay, good. Okay, so what's the multiplication that I need to do? The number n is sitting in x1, and the answer to n minus 1 factorial is sitting in x0. So I need to multiply those. And where do I want to put my answer? Let's put it in x0. Okay, so I'm going to multiply x0 and x1 together. And then the number sitting in x0 is my answer. Okay, and so yes, branch with link, and the link part's important, and I'm going to add 2 instructions. I'm going to add a couple instructions here in a moment. Okay. Okay, so in C, right after we've done this multiplication, are we ready to return? Yeah. Okay, because we've computed n minus 1 factorial. We've got n, we just multiplied them. So we're done. Right? I mean, is there anything left to do to compute the factorial? No. Okay. So at this point, I can return. Okay. So, let me comment this out, because obviously the assembler will complain if I don't. All right. Okay, so we're ready to give this a whirl and see if it works? Okay, any bets as to whether or not it's going to work? Oops. Duh. Oh, yeah, okay. It doesn't like the minus. The dash. All right, line 30. Oh, there we go. Because I'm subtracting 1 from x0 and putting the answer in x0. Yeah, my bad. Okay, good. All right, so fix those little bugs. No big deal. And then now let's link it. Or actually, let me go back up here and add in the debugging. Okay. So I run it. And I get what? I get a segmentation fault. Okay. Why did this happen? Well, we can see what happens. Let's go through GDB and watch what takes place here. Okay. Sure. In our example, I just put in 5. Right. So we should end up getting 120 when all said and done. Right. Just for sake of example. Oh, where? Up here. Right. Okay. Oh, and actually, at the moment, I don't have any stuff to print it. So let's go ahead and add that in real quick, right? Oh yeah, thank you. Yeah. Okay, so that will just print my answer because, so the answer of the factorial is going to come out in x0, but I need it to be in x1 for the sake of printing, because x0 is going to be where I put my format string. So I'm just going to move that data to x1, put the address of the format string in x0 as usual, branch to printf. Okay, now it's still not going to work. Okay, but for reasons that'll become clear in a moment. Okay, so let me reassemble it with the printing in there. Okay, so let's start stepping through this and see why we got that segmentation fault, and then we'll talk about what we have to do to fix it. Okay. Now, I deliberately made sure that we would get the seg fault because I wanted you to see what happens. Okay. Okay, so we're going to step through the instructions, right? So this in line 9 is about to execute. So what is my stack pointer right now? Sorry. Okay, so let's look at all the registers, right? I've got a bunch of garbage in X0 on, and my stack pointer, okay, is 060, right? My program counter is 5E8. I've got some flags set, right, and so on, okay? All right, so after I'm about to execute the instruction to store pair. So if I look at the stack, there's nothing there so far, okay? Because I haven't stored anything to it. I mean, there's data, but this is, you know, garbage. Yeah. My what? Is this better? Yeah. Yeah. Okay. So, right. So if we step, now that instruction is executed, and if I look back at memory, what has been stored to the stack? These two chunks, right? The first and second chunk are a 64-bit number, and the third and fourth are another 64-bit number, right? What did I store? I stored x29 and x30 to the stack. All right, what is x29? That's the frame pointer, which starts as the same value as the stack pointer. Okay, that's the 7F blah, blah, blah 060. Okay, great. And then what is the number in x30? The 4008F4. What is that? Okay, that's the link register. Okay, and basically that's where we have to, when we return to OS control, that's where we would end up going. Okay, so the link register is basically when you go into a subroutine with linking, so when you branch with link, the current value of the program counter gets put in the link register, and the program counter's value gets changed to whatever the address of the subroutine is. When you hit the ret at the other end, the inverse process happens. Okay, and the program counter returns to being what it was before you entered the subroutine plus one line. So you go to the next thing. Okay. Okay, and that's going to become important in a moment. All right, so let's step through this and see what happens. Okay, so what's the next instruction that's going to get executed? I haven't executed it yet. Just going to put the number 5 in x0. And there it is. Okay, I'm about to branch and link to factorial. So again, what is x30 right before I do this? Okay, 8f4, whatever. Okay, immediately after I do that, so I've branched and linked to that routine, what is x30? 5f4, okay, which was, what was the instruction? Okay, what's the instruction where I, where am I? Right here. Okay, this instruction is at line 11, okay, which is memory address whatever, right? And 5F4, okay, is the line immediately after line 11. Okay, so that we know where to go back to. All right, so keep watching. All right, so let's step, 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 step. Okay, let's look at our stack. Now look at our stack. What have I just done to my stack? Yeah, I put the 5 on it. Okay. Right, and it looks like there happens to be some other data there, but whatever. Don't care about it. Right, but the number 5's there. Right, and I'm about to subtract 1 from my from the 5, so I can compute 4 factorial. All right, And now I'm going to branch and link to fact. And here's where the trouble is going to happen, because what is, well, let's look at the registers. What is X30 right now? 5F4. What is it now? Yeah, okay. So the problem is that, did I ever record and save the old value of the link register in this subroutine? No. And so we're sort of stuck. We will never, ever, ever be able to get out of this thing ever again. Okay? All right, so let's step this, or continue stepping it, and see when the issue happens. Okay, so I do a comparison. Okay, so look what's happening. Okay. Oops. So I'm stuck in the recursion, right? It does suck, but I did this deliberately. Okay, and if I hit continue, it's going to seg fault, right? Okay, and the reason that it seg faults is because our stack pointer, okay, our stack pointer, what did we keep doing? We kept pushing things onto the stack, right? And as we recursed, we were pushing even more things onto the stack, okay? And we never successfully stopped the recursion, so we kept just pushing and pushing and pushing and pushing and pushing things onto the stack. Okay, well, eventually, our stack gets so big that it's outside the bounds of what the operating system has allocated to us, and that's when you get a segmentation fault, okay? So memory is segmented, and your program is only permitted to sort of use so much of it, and if you start to go try to access memory out of bounds, you get a seg fault, okay? All right, so how do we fix this? Well, we fix it. Let's look back at our main program. What was the first and last thing we did in a program? We stored the pair x29 and x30 to the stack, and what did we do at the very end of the program? We had to pop it off the stack, okay? We need to do that same thing in our factorial function. Okay, because think about it, our factorial function is almost its own standalone program, right? In the same way that our main function is its own standalone program. Okay, so we need to store those two values to the stack at the very beginning of fact and pop them back off at the very end. Okay, which means we're going to need to restructure our factorial thing here in a little bit. Okay, so I need to add this. Okay, and then I'm going to make some additions here. Okay, I'm going to make a new label called end. Okay, which is going to load the pair back off the stack, and then have the return. Both cases need it, okay? So I could have put a copy of this here and another one there. That would have been acceptable, okay? Or I could have just, you know, done it once and yeah. Okay, so does that kind of make sense? In the same way my main program had to have this load pair, store pair, my subroutine does also, because the subroutine calls itself. Okay, if the subroutine never called itself, we wouldn't have to do this. Okay, because the link register would only get changed once. It would never get nuked again. Okay, but because our subroutine calls itself, we need to do this load and store business. Okay, okay, is that all right? Yeah? All right, let's see if it works. So save it. Oops. All right, assemble, link. Let's just run it first. Ha ha! Success. Okay, so now let's go back through GDB and see this all happening. Now, for the sake of demonstration, let me change this number to 4 instead of 5, just to make it so that we don't have to go quite as far down the rabbit hole. Okay, but it's the same idea. It's just more steps down the rabbit hole. Okay, and let's GDB it. Okay, ready? Okay, so what is the very first line of my program? Okay, the store pair, and its line 9 is sitting at what memory address? 5E8. Okay, so 5E8 is the starting value of my program counter as I execute the program. Okay, and the program counter increments how much each time, by the way? If it starts at 5E8, what's the next value? Because how many spots does it take to store an instruction? 16 watts. How many bits does it take to store any instruction in this architecture? 32. Okay. That's kind of technically lying. Well, okay. So there is a sort of shadow set of instructions. I think that the 64-bit architecture supports it, called thumb, right? If you've got ARM, then maybe you could have thumb. That's what they call it. I'm not making it up, right? That it's actually a bunch of 16-bit instructions, but the instruction set's much more limited. And the idea is that you could accelerate certain parts if you use that, but that's okay. We'll look at OG ARM. Okay. Okay. So it increments by 32 bits, which is how many bytes? 4 bytes. Okay. So if my starting value of the program counter is 4005E8, what's 4 bigger than that? 5E B, right? Because this is in hex. Man, you're killing it. Yeah, yeah. So, okay. All right. So, we have not done yet anything in my program, right? All right. And so, if I look at my registers, right, what do I see? Well, my program counter is this because I'm about to execute that instruction, right? My original stack pointer is this. I haven't changed it yet. And my link register is, okay, 904, whatever. Okay, so that's where I'll return control to the OS. Okay, all right, so let's start stepping through the instructions. So I just put stuff on the stack. And looky, there it is on the stack pointer. Okay, so the two things I just stored to the stack are x29, which is my frame pointer. That's sort of the original value of the stack pointer. We'll talk about the frame pointer later. And x30, which is the value that was inside the link register. Okay. Okay, and it was blah, 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 904, whatever. Okay, great. All right, and Okay, so I'm about to load the number 4 in. Now the number 4 is in the thing. Okay, so let's look at x0 has the number 4 in it. Okay, that makes sense. And x30, which is my link register, has 904 in it, right? I stored that value to the stack, but it's still in the register. Okay, now what I'm about to do is branch and link. Okay, so what that's going to do is it's going to take the current value in the program counter plus 4, right, which would be the instruction immediately after BL fact in my program, and it's going to put that into the link register. Okay, so if I step, I'm now inside my subroutine. And what is x30 now? 5F4. That was the instruction immediately after the BL thing. Okay, so that's where I would go back to when I finish with the recursion. Okay, when the whole thing is done. Okay, good. All right, so now, what did I do this time? What did we add to our program? We added another load store pair, right, for our link register and stuff. Okay, so I'm about to, well, I just actually did it. This guy here just did it, okay? It just put x29 and x30 onto the stack. Okay, and now if I look at the stack pointer, what do I see here? Okay, what's this? That was the value of the link register from the main program. This is the value that I just stored when I came into my first instance of the fact function. And if I keep stepping, okay, I'm going to do the comparison. I'm going to branch. I'm going to store the number. Okay, I'm going to subtract. Okay, so here's where I want to stop. What's x30? Still 5F4. Okay. And what's on my stack? What's on my stack? Yeah, okay. The very bottom line that I've highlighted was the first time we pushed stuff on the stack. That was in main. The next one is the time I stored the pair x29 and x30 at the top of my fact routine. And then I just pushed the number 4 onto the stack. And there it is, 4. Okay, good? All right, so I'm paying attention to this number, and this number. All right, and now let me step. Okay, so the instruction I just executed was to branch and link to fact. And now look at what my link register is, 630. So when I hit a ret instruction, what happens is that value is transferred to the program counter. That tells me where to go back to. Okay. Okay. So let's just follow the rabbit hole here. Okay. So if I continue, oops, that is not what I meant to hit. I am sorry, guys. Okay, what's on my stack now? Because this is where we were a second ago. I just sort of teleported us back. What do we see at our stack now? What's that first value? Blah, 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 060. That was our frame pointer. Okay, whatever. But what do we see there? The 400630. That was the old value of the link register, right? Okay. And if I continue this, or I'm not going to continue, I'm going to keep stepping, right? All right, go to the recursive case, store a number onto the stack. Subtract 1, branch and link to fact. But before I do that, what's on my stack now? Now, in addition to 4, I have 3 in my stack, right? So I've got 4, I also have 3. Okay, and look at what's sitting over there next to it, a link value. Okay, and so let's keep going. All right, store pair. Well, what's on my stack now? There's all my stack. What do I see on my stack? Link, 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 link values. Okay, but actually, which ones am I paying attention to? Does this DD0 or this DB0, do they actually have any meaning? No, okay, those were just things that happen to be there in memory, okay? So what I'm paying attention to is link value, link value, link, and then value, okay? Now, notice, by the way, what's the, notice that these two links are 630. Why does that make sense? They're the same thing, right? Well, what is that memory address 630? It's the instruction immediately after the branch and link. Okay, well, we're running the same subroutine. So of course, what's after the BL fact one time is the same thing as after it the second time, right? It's the same code. Okay, all right, so let's keep going. Okay, comparison, recursive case, store, branch and link to fact. Let's look at our stack right before that. And now look what we got. What we got, oops. Well, I see the number 2 up there. What about you guys? Yeah? Okay. All right, so let's continue. All right, so I just pushed more stuff onto the stack. And notice what I've got now. Link value, 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 value. Okay, but what's about to happen? Well, first off, what's in X0 now? 1. What's in X1? Okay, is 1 less than okay, so 1 is less than or equal to 1, right? Which means, will this branch get executed? No, okay, because 1 is not greater than 1. Okay, and you got to be careful when you think about the logic of this, because otherwise you might miss that edge case. Okay, okay, so are we going to jump to the recursive case this time? No, we won't. Okay, which means, where are we going to go? Our base case, which was just to put the answer 1 in the register, and branch to end. Okay, what does end do? We're going to start unwinding the stack. Okay, so before I do that, let's look at sort of the final value of the stack. Okay, so it was all of, I think, this, right? So what did we start doing when we went through this? Push, 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 push. We got down to the bottom, and now the recursion is going to start unwinding, and we're going to start popping off values. Okay, and in particular, did we ever hit a mul instruction when we were going through this? No. Okay, not yet. We're about to hit all those multiplications. Okay, so now we're going to start popping off the stack, and these link register values, because we've stored them, okay, we know how to sort of follow the breadcrumbs back to get out of the rabbit hole. Okay, all right, so if I start stepping, I hit the return, I go back. Ah, now I'm about to pop something off the stack. What am I about to pop off the stack? Okay, I'm about to pop off the 2, I think. Yes, okay. I'm about to pop a 2 off of the stack, right? Well, there she is. Okay, and so now what's sitting in register 1? Register 0 is 1, and register 1 is 2, and what am I about to do with those? Multiply them. And now, shockingly, 2 is in register 2. Okay, branch to end, pop off the thing, return, and now let's look at our stack. Now what's our stack? Yeah, 3 is on top or bottom, depending on how you want to look at it, right? So this is sort of the annoying thing about the terminology, right? Oh, the number 3 is actually at the bottom of the stack, okay? In the sense that it's in the lowest memory address, okay? But if I list the memory addresses in order, I put the lowest one at the top, and so in a sense, it's at the top of the stack, okay? So is that annoying that the terminology is going to be always backwards from whatever you are? Yes, get over it, okay? I mean, I know it's 8 in the morning or 9 in the morning, right? Oh goodness, how time flies. Okay, so now we're just going to be popping off the stack, right? And so let's keep stepping, multiply, branch, all right? What's in X0? 6. What's in X0 now? 24, right? Because 6 times 4 is 24. And are we done? We got one more, and that popped us off because I did 4 factorial because I changed it from 5 to 4 just so we wouldn't keep doing this 50 billion times. Okay. And there we go. Right? So we just popped back to the main routine. We took the number 24, we copied it over to X1. We're about to load the address of the format string. We're going to branch to printf. We're going to load our thing off. It printed the number 24. That's right there. Okay. Load 0 to hand back to the operating system. Return to the operating system, and that's it. We're done. Right? Okay. So that's how recursion really works. Okay. It's all about storing your link register as you go. Okay. And using the stack judiciously to store intermediate data as you go. Now, in the case of the in the factorial, right, this was sort of singly layered recursive in the sense that what was 5 factorial? 5 times whatever 4 factorial was, okay? But in the case of the Fibonacci's, what do you have to do? What's Fibonacci number n? The previous 2 added together, okay? And what that means is that you're going to have to do something like, let's say you call your function fib, right? If fn is fn minus 1 plus fn minus 2, right? In order to compute this, you're going to have to put n minus 1 in the register x0 and then branch and link to your fib function. And then when you come back, you're also going to have to somehow put n minus 2 in x0 and branch and link this one to fib. And you're going to have to store the answer to the stack here and store it to the right. And so you're going to have a little bit more stack management to worry about, okay? Because you're going to have multiple partial answers that you've got to keep track of. Okay, so it'll be a little different than the factorial, but that's sort of the still starting similarly, okay? Also with the Fibonacci case, well, like with any recursion, we can't recurse indefinitely, okay? So we need a base case, right? What was our base case for the factorials? Yeah, being less than or equal to 1, that's 0 or 1, okay? Or technically, if I were a dumbass and put in like -7, then this program would tell me that -7 factorial is 1, okay? Now, -7 factorial is not defined, but the program would give me 1 back, okay? Fine. With the Fibonacci's, what were our base cases, plural? 1 and 1 were our base cases. So if the number of the factorial that you're, or sorry, the Fibonacci, if you're asking for Fibonacci number 1 or Fibonacci number 2, what's the answer? 1. Otherwise, you do the recursion. Okay? Yeah. Now, that said, because I've gotten a few questions about this, how many of you guys started your Fibonacci's with 0 and 1 instead of 1 and 1? Okay, that's fine. You get the same sequence eventually. It's just where do you start with it, okay? So depending on who you ask, or like maybe in certain math books, they might start with 0 instead of 1. It doesn't really matter. Just pick something and stick with it. Okay, the point though is that you're going to be generating, eventually you'll start to see 1, 1, 2, 3, 5, 8, and so on, okay? Which, by the way, is the sequence of numbers in the movie Contact that tells them that they've actually gotten a signal from extraterrestrials. Okay, yeah, see what I did there? The secret to good comedy is to go back to an earlier part of your routine, right? Yeah, that was completely unplanned, by the way, okay? Yeah, so make sure you tip your waitresses. I'll be here all week. We've got a great gin and tonic special tonight. Kidding. Wally's, yeah. Okay, so make sense? All right, so the very last thing I wanted to just mention, just briefly, okay, is relative addressing of memory, okay? So let me go back to Jeannie, and I'm just going to type a line here down at the bottom, and I'll delete it later. Okay, so if I want to do string processing, okay, in C, how did we handle a string? If we had a string and I wanted the first element in it, I would do this, right? And if I wanted the second element, I would do that, and so on, okay? So the brackety thing for strings in C allowed me to move character by character through it, okay? And essentially what we want to do is, what's sort of the equivalent looking operation here in assembly for doing relative addressing, okay? And so here's the, well, let me just write it on the board, okay? I could do something like LDR, destination always has to go wherever, okay? But if I say something like this, what it'll do is it'll say, okay, X1, go to X1, look at what's in X1, okay? It's some sort of number, right? 64-bit number. Interpret that 64-bit number as if it's a memory address. Go out to that memory address, whatever you find, take that thing and put it in X0. Okay? And then there's another variation, which is if we do something like this, LDR X0, X1, X2, this will say, okay, go out to X1, there's a number there, find it. There's a number in X2, add that to whatever you found in X1. Interpret that as a memory address, and take whatever is in that memory address and put it in X0. Okay, so here's the brilliant thing. What about if we make this a single byte, so a number, right? 1, 2, 3. Well, what we can do is we can say, all right, if X1 is the starting memory address of a string, and we make X2 equal to 0, then that'll get me the first byte of the memory address, or of the string. And if I increment X2, then I can scan through character by character to get more and more things. Okay. Now there's a few details to this, which we'll talk about Tuesday, I guess, that you guys are going to find really stupid. But if you've ever ordered something from Amazon, um, you know what happens if you get something from Amazon? You order like this little thing that's like a book. You order a book from Amazon, and what does it come in? A giant box that's like grossly exceeds the size necessary to have stored that package. Okay, because there's going to be something sort of like that here. But I think you guys will like it. All right, and on that note, have a great Thursday.